precipitate form.
Let me write the equation up here on the board. Do you mind reading it to me?
Yeah, the formula or whatever.
Yeah.
Okay, so it's PB parentheses ClO3 in parentheses 2 and then aqueous, if you want that.
Yeah.
Plus 2 sodium iodide aqueous. And then it goes to PBI2.
And that's solid, right?
Plus 2 NaClO3 aqueous.
Okay. So, here's our reaction, right? And then it tells you, it gives you some masses. What are all those?
It says, it doesn't give me, it gives liters, so it says, was the mass of precipitate that will form if 1.5 liters of concentrated PbClO3 is mixed with 0.85 liters of 0.23 molarity sodium iodide.
Like that?
Yeah.
And it wants to know the mass of the PBI2, right? That's the precipitate.
Right.
So this is what we're looking for. This is what we have.
Okay.
And it's 0.8 liters of 0.2 molar sodium iodide.
Yep.
Okay. I think the best place to start is probably with the sodium iodide, because we can just kind of get rid of all these numbers and say this is how many moles we have. Then we can say how many moles of this do we have.
Okay.
So if we have 0.23 molar, that means 0.23 moles per 1 liter, right?
Yeah.
But we have 0.85 liters. So would that work?
Yeah. So that would give us 0.1955 moles.
Yeah. Okay. And then we could do something similar with this one. We have, oh, it said concentrated, right? So by
Yeah.
by concentrated, do they want us to assume 1 molar? Or sorry, not 1 molar. I don't know, because in OChem, concentrated sulfuric acid is like 60%, you know? Do they tell you what concentrated really means?
It says, but we know it's an okay. So we don't have enough information to calculate the moles of the other reactant, PbClO3, but we know it is in excess because its volume 1.5 liter and molarity concentrated are both larger than that of sodium iodide.
Yeah, okay. That makes sense. So they don't even expect us to solve for how many moles of this we have.
Okay.
Because they're assuming that we realize you have a lot more volume and a much higher concentration. This just said it was concentrated, right?
Right.
Which we just abbreviate conc.
So what that's basically saying is just that, like, it's a high molarity, is that what that basically means? But we don't know, like,
Yeah.
how high.
Do you remember when you had to find like limiting reagents? Like which one, it gives you an equation like
Yeah.
this and it says, okay, which one is going to be limiting? And it's you can calculate percent yield of whatever based on your limiting reagent, not the reagent in excess.
Yeah.
So this is just it's giving us these like a lot bigger volume, and it's saying it's concentrated, and then we should be able to say, okay, if those things are true, that one's definitely going to be excess. This one is going to be my limiting reagent.
Okay.
And so that one is going to determine how much of this forms.
Okay.
Because you could have all of the wood in the world, but if you only have this much oxygen,
Right.
there's only so much of that that's going to burn. But if you have excess oxygen, then all of that will burn. We have excess of this. This is our limiting, so this determines how much is actually going to react.
Okay.
So there's going to be plenty of this left over, but none of this. So I wasn't thinking in those terms, but that makes sense now. Does it help? Okay.
Yeah, I think that makes sense.
So if we know that we have this many moles of our limiting reagent, we can just look up here, because first of all, is this balanced? That's always something to ask yourself. Sometimes they'll give it to you balanced, and other times they may expect you to balance it. We can look and say, I don't know if we just start with lead. Lead looks balanced. ClO3 is balanced. 2 sodium over here, 2 sodium over there, 2 iodide, 2 iodide. So yeah, okay, it's balanced. And then once we know it's balanced, we can say this reacts. 2 moles for every 2 moles of this that react, we get 1 mole of that. So they react in a 2-to-1 ratio. If we have this many moles, and it said it goes to completion, right?
Right.
Which in real life, that doesn't really happen.
Yeah.
But, we don't like real life.
Yeah.
So it's better to talk in these terms. So, I shouldn't say that. We do like real life, but you know what I mean.
Yeah, I know.
So 0.1955 moles of sodium iodide.
So then we can do a molar ratio, right? And do,
Yes.
So we do 2 moles of sodium iodide on the bottom, and then on top 1 mole of PbI2.
Okay.
And that's like 0.0975.
Moles of our precipitate, right?
Right.
PbI2. I guess you should say solid.
And then from there, then we just need the molecular weight, right?
Yeah, because it wants mass, right? Yeah.
So,
Guess I shouldn't have boxed it.
well, I was thinking too. I was thinking the same, and then
So it's nice to write down what you want,
Yeah.
because sometimes you forget what you're looking
for
for.
the text, always like question mark, question mark.
Yeah, no, it's helpful.
All right, so the atomic mass of lead is 207.2, and iodide, here I can just,
Oh, I'm sorry.
126. Okay, so 461 is the molecular mass.
I guess we could have made this one big long unit conversion, right?
Right.
But since we forgot what we were looking for, we broke
Yeah.
it into 2.
That's 45.06. Or 45.1, which is the right answer.
Does the process make sense?
Yeah, I think it does. I'm gonna take a picture of it just to